So it's my great pleasure to be able to be here to talk during this 15th birthday party for the Museum of the Earth, and also to talk to you about this book right here is the one he didn't show, which is Art Bloom's book on his guidebook to the local geology here. And I'll try to talk to you a little bit about a few of the highlights of things I learned from this book today. But the book is over 200 pages long, so I'm only going to be able to scratch the surface just a little bit. But let me just talk a little bit about art and the history of this book. So Professor Emeritus Art Bloom and his wife Donna, who is here in the audience today, moved to Ithaca in 1960. And over his something on like 57, 58 years living in Ithaca, he did a lot of research at Cornell University around the world, but he also acquired a lot of knowledge about the local geology here, a really unique storehouse of information. And over many years, he wrote up this information in a book form, and during his later years, we just helped him to get that published. And John Hendricks here also played a big role in trying to get this book actually that came out in June of this year, right here. And of course, lots of other people helped us to get this to this point. We made lots of figures. There's beautiful color figures in this book that were made by several of the people over here. Art's family and Warren Allman and lots of other people played a role in getting this book published. So we have a lot of people to thank, and it's a fantastic resource. And I guess the first run I'm hearing is, I'm thinking it's going to be sold out by the end of the year. So hopefully they'll start another run soon. But I have to talk about this book in the context of understanding Ithaca. So of course Ithaca's byline, Ithaca's tourist mark is Ithaca is Gorges, which has a geologic bent, and his study of the local landscape here has a long history as well. And one of the key characters I need to mention is this gentleman right here named Oscar von Engeln. Oh, let's go back. Seen here developing pictures during one of the expeditions he went on in the early 20th century to Alaska. And this is a picture that appeared in National Geographic. And he also was interested in the local geology and the landscapes of the region, as well as studying other glaciated areas. And he wrote the best book on the local geology that existed up until Art's book, which was called The Finger Lakes Region, Its Origin in Nature. It was originally published in 1961. Right here is a picture with Taganek Falls on the cover. Went through several editions back in the 60s. And then Professor Bloom put his cover on the re-release that came out in 1988. And this book, for over 60 years was the best local source, but was sort of written in the language of the early 20th century when Dr. von Engeln received his education at Cornell, both undergraduate and graduate degrees. And so I talked to many people who I'd go out to restaurants and people would say when they knew I was a geologist, is there a good accessible book about the local geology? And I have to say that this book was not always the most accessible. It was sort of written in an older language, but Art's book I can heartily recommend, along with this book that you can find upstairs, which is written by people here at PRI, which is more of a very short introduction, and Art's book sort of goes into a little greater depth in a lot of those things. I should mention that von Engeln has his mark on the local landscape as well, in that there is the von Engeln Preserve in Malloryville over in the town of Dryden, which is a place where he loved to take students on field trips, which is features an esker, which is sort of a subglacial river, a prominent geomorphic feature in this area. And so his bequest helped to create this park where we can see that feature still today. And the other person that I should mention today is Oscar von Engeln's professor and instructor, which was a guy named Ralph Stockman Tarr, who was a Cornell professor starting in 1892 and was there for 20 years. Professor Tarr led these expeditions to Alaska and also studied the local geology, wrote some of the seminal papers that Professor Bloom was very familiar with all this work and cites it throughout his book. And so Art's book has a deep history of leading back to knowledge built up by von Engeln and Tarr and updating it to the modern day. So So let's move on to talk about what Art's book is. So I'm going to focus on three little vignettes, three little questions that I found particularly interesting Art's take on answering these questions. And this will sort of give you a flavor of the types of things that he talks about in the book. Again, his book has a great deal of depth. It discusses the history of the local area, where the bedrocks came from, the history of the glaciations, and then he talks about some site-specific field trips that you can take to various sites throughout the area. And so I sort of drew on that together to focus on three different questions. So the first part, I'll talk a little bit about the story of the Finger Lakes. And we have these 11 Finger Lakes right here. And the two biggest ones are in the middle. And so there's a geologic reason for why that might be. And I'll try to outline what that is. And I'll also talk about how Ithaca is gorges. We have lots of gorges here. And when you visit several of these ones, you can't help but notice that there are lots of differences between the different gorges. And again, that story is also related to the bedrock, the rock that makes up those gorges and how that rock was formed. And so we'll talk about, for example, differences between Treman and State Park and Watkins Glen State Park. And then we'll talk about some of the evidence for multiple glaciations that explain some of the differences as you walk up gorges, whether it be in Treman State Park or in Fall Creek Valley. Why do the gorges change from these narrow rock-controlled channels to wider open spaces? And again, that has a story that relates to the history of glaciations in the area. All right, so let's start at the beginning with the bedrock, which is where Art starts his book, which is what are the rocks that the region is made out of. And we have to go back to the paleo environment that existed here in the Middle Devonian time period, 385 million years ago, when we were near the equator here in New York in a shallow tropical sea that made up this Appalachian Basin region. And this region was right next to the Acadian mountain belt. And so you can see this large mountain belt like the Andes today, which was shedding sediments to the west that formed this large Catskill Delta. And this Catskill Delta had a form that looked something like this, right, with the large mountains and the streams, and they were dropping off the sort of larger sediments near the coastlines and the finer and finer sediments as you go further and further offshore. And so this is an important system of sediments that we can see. Basically, we as we go from west to east across New York State, we go from the fine-grained offshore sediments to the coarser-grained clastic materials as we approach the Catskills in the east. And this has an important change in the bedrock that makes up the region that we can see reflected in the gorges and in how those gorges were subsequently eroded. So this is just showing an example of this thing that was called the Catskill Delta, this big pile of debris that washed off of the Acadian mountains that were located over here to the east. And as you would expect, that there was more sediment eroded on the eastern part. And so this is a sort of an east-west cross-section that shows that this sediment pile was thicker in the east, almost 3 kilometers thick. And then when you get out to Buffalo, you're getting more to the western part of the state, you're getting into the thinner and thinner parts where it was, in this case, only about a kilometer thick here, and this says near Jamestown, for example. And so the Ithaca area here is somewhere in this vicinity. These are the rocks that are exposed at the surface in the Ithaca area. And so we were in a pretty thick part of the sequence, not in the coarsest grained materials and not in the finest grained materials, but in an area that was thick and relatively fine-grained and weak. And so that's an important part of the story in terms of looking at the Finger Lakes and how they were eroded subsequently. So this is just giving you, again, a sense of looking at these Devonian rocks that are exposed at the surface throughout all of the area here in the southern tier. As you go further to the north, you're getting to the older and older rocks that are exposed because these rocks are dipping to the south, and they sort of have this trend to them. And if we look at, again, this Catskill Delta in map view, again, what we expect is that we have sort of more classic materials like sandstones to the east and more shaly materials as we go further and further west. Again, reflecting this change from material that just is eroding off the Acadian mountains to things that are going further and further offshore where this finer material is getting deposited. All right, so that is the bedrock story. That's the type of rocks that are around here. May all look similarly like gray rocks, but there are, if you look closely, subtle differences in the size of the particles inside there that has an important implication for how easily those rocks erode. Because we had a major episode of erosion that happened during the series of ice ages. So this is showing the last glacial maximum about 24,000 years ago, showing you where the termination of this ice sheet was. And as that ice came through the region, it of course left some sediment deposits and also caused erosion. And one of the factors of that erosion was carving out the former river channels that made up the Finger Lakes region, as well as, and so this is just showing you an example of the carving that was done of the Finger Lakes. And so this is showing a cross-section across these 11 Finger Lakes, showing you how the depth to the water that's seen here in the blue. And you can see that the two largest Finger Lakes actually have the bottom of those lakes are below sea level, which is shown over here. But also when people went through with seismic studies on boats to figure out where is the bottom of the sediment, they realized that that was even deeper, that the glaciers had actually carved several hundred meters below sea level in the two central Finger Lakes, and had carved much deeper than the water level in several of the other lakes. So these glaciers and the subglacial water underneath them were very effective at eroding away these lakes. And the relationship between this bedrock that we saw in this map over here and this erosion allowed these two central Finger Lakes to be the deepest. Again, looking at this cross-section here, there was a lot of weak sediment to be eroded, and if you go further to the east, there's a lot of sediment, but it was harder to erode. If you go further to the west, there wasn't as much sediment to erode, but these two central Finger Lakes, and in fact all these sort of Finger Lakes in the middle, eroded to the deepest levels because of this bedrock that existed from the time that the sediment was laid down in the Devonian time period. So the size of these lakes and how deep they eroded is related to the geologic history. And another evidence of the bedrock, the rocks as they were formed in these Devonian seas having an important control, also is related to the Onondaga limestone. So we mentioned back here that there's a lot of sandstone and shale throughout the region, but there were also a couple of episodes when we had reefs and limestone was deposited across the area, and that limestone has been super important as a building material throughout the Finger Lakes area. But that also is a stronger material that is harder to erode and is thought to be one of the reasons that the Finger Lakes have a bottom that is where it is. And that's related to the location of this Onondaga limestone. So this is showing you a cross-section through Cayuga Lake, where again, this is sort of the lake fill sediments in yellow. But when the glaciers were coming through, what they saw in the bottom was this limestone. And they had a hard time eroding through that limestone, and that's sort of why the Finger Lakes didn't get deeper than they were, is when they hit this harder rock there. So that's sort of the base of many of the different Finger Lakes throughout the region. All right, so part of the story is that bedrock is the destiny in terms of understanding variations we see between the Finger Lakes. But the bedrock is destiny also in describing the differences we see between the different gorges. So we'll talk a little bit about several of these different gorges here. So we are over here at the Museum of the Earth. We'll talk a little bit about Ludlowville Falls over here near Lansing. We'll talk about Taganek Falls State Park, Enfield Glen or Treeman State Park down here, Buttermilk Falls, Ithaca Falls, and we'll talk about Watkins Glen over on Seneca Lake as well, just comparing and contrasting these. So what we expect is that there will be slightly different rocks exposed in each of these parks, in part as we have this variation between east and west, with a bigger variation. There's not so much east-west variation between these parks, but by the time you get over to Seneca Lake, you're in a different area. But you also have some differences because these rocks are dipping to the south between parks that are further to the north and further to the south. All right, so the basic story behind the gorges is that as the glaciers came through and made these very deep Finger Lakes cutting through the old river valleys, is that they sort of over-steepened the walls, and when they retreated away, they left these rivers that were pouring into the previous river basin here, high and dry, and so these things have cut backwards through time, making the local gorges in the area. And so, but it's interesting to note that not all of these gorges have been cut out in the same way, right? As I'll show you pictures in a second, at Taganik Falls, you have a single large waterfall, while if you look at Fall Creek or Cascadilla Creek or some of the other areas, you have multiple cascades going up the river. And so this is just showing you some examples of these different gorges. Here's Taganik Falls with its single large waterfall that, while here is Buttermilk Falls, which is more like a series of cascades, and things like Watkins Glen or Fall Creek, where there's a series of smaller waterfalls going up the gorge. And again, bedrock is the destiny for explaining some of the differences between these different gorges. So this is showing you the list of the different formations through the area, where you can sort of see some trends between shaly rocks appearing during the earlier times and appearing to be more and more sandstones as time goes by. And this is showing you sort of which are the rocks that are exposed in each of these different gorges. So I think I've got a picture here of Ludlowville. Ludlowville Falls has a nice cap rock waterfall because it has, one of the rare instances of a limestone formation in the Finger Lakes, this Tully limestone that is hard to erode and is well preserved and makes this cap rock limestone waterfall, and the shale beneath it is more easily eroded away. And Art has a beautiful discussion in his book talking about speculations on what will be the future for Ludlowville Falls in terms of will this thing form a natural bridge, will the waterfall collapse? A lot of interesting calculations have been done. So this is one of the few examples of a capstone waterfall using the Tully limestone. There's also at the base of Taganik Falls State Park, as you just start walking up, there's a small waterfall that's made out of the same formation. But most of the waterfalls that we see in the area are not this sort of cap rock limestone. They're all related to shale or sandstone formations, and can have this sort of beautiful stair-step pattern or a cascading pattern. Another prominent difference between the different gorges, if you look closely, is the presence or absence of joints. So let me just say a brief comment about joints. If you've walked in the local gorges around here, you've seen these joints. These are these fractures in the rocks. They're primarily vertical. They're often at right angles here in the Finger Lakes area around Ithaca. And these joints are formed during mountain building episodes that form the Appalachian Mountains. So this is all due to pressure that was hundreds of kilometers away that was transmitted through the rocks. Still didn't cause a lot of mountain building in this region, but did cause enough stress to cause these sort of fractures. And so there's some nice pictures in Art's book that show the orientation of these joints throughout the whole of New York State and how they move in concert with the trend of the Appalachian Mountains. So these joints are formed during this collisional process, but they form easier in some rocks than in other rocks. In particular, when you have these fine-grained shale rocks, they don't form very easily, and you usually need something that's a little more like a siltstone or sandstone to be able to form these types of joints. And that's one of the key reasons you have the difference between the formation of joints here at Treman State Park in Enfield Glen versus not having very many joints here in Watkins Glen. Again, as you go further to the west, rocks get a little shalier, get finer grained particles within them, and make it harder to form joints. So they felt the same mountain building process that was going on down in Pennsylvania, but the rocks here didn't break as easily into forming those joints in this location as they did here. So it's just very different types of erosion processes that are happening in these two areas, where here it's just the abrasion of the water with sediments making the gorge, and here you have a little bit of access of the joints helping to break off the rocks and pluck them with this sort of beautiful pattern of erosion that happens in Enfield Glen. All right, so I guess, here's a picture from Art's book that sort of shows the orientation of these joints across the state. And again, this is just showing you here is where Enfield Glen is, here near Cayuga Lake, and Watkins Glen on Lake Seneca, showing that we expect a difference as you get further away from the source of the Catskill Delta into the more shaly rocks. And that sort of explains why we have joints in this area, but fewer joints as you go further to the west. All right, so another beautiful thing that's in Art's book is former professor Brian Isaacs made some beautiful maps using new data from Lidar. And so Lidar is locally has been collected off of airplanes, sending down a light beam. And this light beam can be used to record the reflections off the top of the trees and off of the ground. And so this is a way that you can actually remove the effect of trees to see the landscape underneath. And that works beautifully. And here's just an example of the Von Engeln Preserve that I talked about earlier with the eskers in it. And you can see that it's covered in trees. But with the LiDAR images, when we can take those trees off, you can see these geologic features below. And so here's the esker that we talked about before, as well as several other kettle and other glacially carved features in this preserve. And so using this LiDAR, Brian has made several beautiful pictures for the book where we can look at the shape of the gorges. Just to give you another sense as to what you can see in this type of LiDAR is, here's an image of Ithaca and the region to the northeast, going up through Varna and toward the town of Dryden. And I think you can see even in this sort of zoomed out version, there's some beautifully glacially carved features in this area. You can actually see sort of scours where the glaciers came down from the north and then took a head off to the east up Fall Creek. You can sort of see these nice little grooves here. The other thing that you can see, that you can appreciate from the LiDAR that you can't always see so easily on the ground, are a couple of features that are called moraines, that as the glacier pushes sediment up and to its end, it usually leaves a little mound of sediment at its terminus. And you can see some nice, beautiful moraines that come through this area here, like one's over here, you got another one over here. And again, this is sort of seen more easily on this LiDAR where you can strip away the trees and you can go confirm that these things exist when you go visit them on the ground. All right, so there's a couple of beautiful pictures like that in Art's book to illustrate the points that Art is making about the geology. But these LiDAR help us to motivate a couple more questions that we can observe on the ground, but we can also appreciate through looking with these data. And that is to look at the shape of the gorges and how they are different from one place to another. And sort of ask the question, well, what were the reasons? Is it bedrock control? Is it controlled by the rivers? This is showing you an example of Tegonic. So here's the lower part of Tegonic Park. We go up the gorge when you're hiking, and you come up here to the waterfall. Then you can see here is the upper gorge. Oh, and here is that little waterfall I showed you before that's in the Tully Limestone. Here is showing the Cornell campus, showing Cascadilla Creek, which again has a beautiful trail that you can walk up here through the steep part of the gorge to the area where it's a little bit wider. And similarly over here on Fall Creek, where you can walk between Forest Home area through a very narrow gorge to Beebe Lake, back to a narrow gorge. And this sort of raises the question, well, why are there these differences as you walk up the gorges in a creek like Fall Creek? Why do you go from an area where it's very narrow, rock confined, to an area that's much wider? Let's see, another good example of that, I guess we'll talk about next, is at Enfield Glen. And so another good local example that the LiDAR shows is Buttermilk Falls State Park, where here you have the current park, and here's the Buttermilk Falls is down here. You can go on a nice gorge trail up through this area. But when looking at the LiDAR, you can see, hey, look, there is another gorge right next to this that you may not appreciate with all the trees that currently cover it up. And this is one of several lines of evidence that we'll go through that this area was not glaciated one time. This area has had many glaciations, and the streams didn't always find the same place that they had excavated before. Art has a great line in the book where he says, basically, it must be very frustrating to be a river here in the Finger Lakes area, where you start to cut down one gorge, and then a glacier comes through and fills it up, and you got to go and recut it down, and you may not always find the place where you started before. And so this is just showing you an example of the number of glaciations we think there have been even over the last 10,000 years. So this is showing you a map of sort of glacial deposits between Cochrane, Ontario, going down to Cincinnati, Ohio. And this is showing you, places where they've dated where these are. So here's Cincinnati, here is Cochrane, showing you that the glaciers didn't just come once and go, that they came down, they retreated some, re-advanced, retreated, re-advanced, that there were multiple episodes of the glaciers coming and going, and this is just over the last glacial cycle back to the last glacial maximum here, and this is sort of cycle repeated for several million years. So we don't really know if the glaciers have been through here 5, 10, 20 times. We don't have a lot of good records, but we do know that it's been multiple times, and that these cycles of multiple glaciations have impacts on the shape of our local gorges. And another important part of the story for looking at multiple gorges is that multiple glaciations is that these glaciers, every time they come, do a little bit of erosion, also leave some sediment junk behind with them. And one of the most impressive episodes is the last large-scale re-advance that happened, which was associated with what's called the Valley Heads moraine time period. And so the edge of the glacier is sort of inferred to be something like this, at a point about 13,000 years ago. And you can visualize this very clearly driving through the gorge. It's called the Valley Heads moraine because this pile of debris that was deposited serves as the divide between streams that run to the north to the St. Lawrence River and through the Great Lakes region, and go to the south through the Susquehanna River to the Chesapeake Bay. So you sort of go down in some of these valleys around here, and there's just a very, it's not the continental divide of Colorado. It is a very small little pile of sediment that has been put by the glaciers that sort of no longer allows the streams to cut through the whole region. And it's very impressive. This is, for an example, driving down towards Spencer through Inlet Valley. You sort of go up this pile of debris. You see all of this rough terrain that was underneath the ice that sort of terminates very abruptly and then becomes what's a smooth outwash plain. So basically the idea is that the edge of the glacier was right here. You had streams coming off the glacier, making a nice smooth surface to the valley, and underneath here you just had blocks of ice and rock that were intermixed together, making a much more coarse surface. Another spectacular example of this place at the edge of the Valley Head moraine is over in Tully, where if you're driving on Interstate 81, you drive into the north through the smooth terrain through Cortland, up through Tully, and then all of a sudden the valley to your, if you're driving to the north, the valley to your west drops out from you and shows you again the edge of the glacier was right here, and it was washing off a bunch of smooth sediment onto this smooth outwash plain. And here, if you drive through here, you'll see there's a series of small little kettle lakes, mounds of debris, all related to sort of this moraine that was deposited at the edge of the glacier. All right, and that's just showing you where the edge of that moraine was. So the key point is that each time the glaciers came through, they left a bunch of debris behind. They left it at their moraines, and they also used it to fill up some of these old valleys. And so here's a great story that can be told about this multiple episodes of glaciation here at Treman State Park and Enfield Glen. So here's just showing you through the Lidar that if you're walking through the lower part of the park, you often see wide valleys until you get up to Lucifer Falls and beyond, and the valley closes in on you. It becomes much more restricted. And that's partly a story of the old creek that used to be here had cut down this valley in previous glaciations, but it got trapped in this other part and wasn't able to find its original valley the last time around. And so I'll try to show you a little cartoon of that here. So here's the current state of affairs, the lower valley here at Treman State Park, going up to Lucifer Falls, and the narrow little valley. So what we imagine is that at the end of the last, in the last glacial in the period that's called the interglacial, between glacial periods when we had the streams that came through and cut down, we infer that the stream had an orientation something like this. that it was similar in the lower valley to what it is today, but in the upper valley, it had a little bit of a deviation. And so what happened after the last glaciers came through, they filled that whole thing up with till and other debris. And so the stream had to form again and formed in more or less the same place and started to cut through that glacial sediment. But it sort of made a little bit of a wrong turn right here. And it started to cut through the weak glacial sediment in a different spot, and it sort of got caught in that area. It couldn't jump out and find the other area because it had eroded itself away. And so what that means is that as it got caught in that glacial debris, as it cut down over here, as it cut through all of the old glacial debris, it eventually got to fresh bedrock. And so it couldn't jump back into its old gorge, so it had to just start cutting through that bedrock. And so that's basically how we got this nice little Enfield glen up here, cutting through new bedrock in a much narrower gorge than down here where it had found its previous work. It had found that previous area that it had excavated a wider valley through. And so that's why, so here's again another picture of Enfield Glen, this narrow little valley that's probably only formed in the last 12,000 years, while the wider valley down here formed over several different glacial cycles. It had several different times between the glaciations to excavate this part of the canyon. All right, so this is just telling you all the different steps here. So the story of multiple glaciations and buried gorges is a story that's repeated throughout New York State. Another famous example, if you've been to Niagara Falls and to Niagara Gorge, is you might be familiar with the Whirlpool Basin over on the Canadian side. And that Whirlpool Basin, again, is evidence of a previous gorge where the Niagara River, during a previous interglacial time period, had gone in this direction. It got filled over, and so it didn't find that old gorge as it was working its way down through the new till, started over here, but as it came around this corner, it excavated a little bit of that buried gorge. And so there's a little bit of a whirlpool there as the falls migrated up to its current location. Similarly, in Fall Creek Gorge, you've got the same story. As I mentioned before, you've got Beebe Lake here, which is a nice wide part of the stream, but then you've got this very narrow gorge that leads into Forest Home. And again, this is another story of, this was presumed to be the channel before the last glaciation, and as the stream came down last time, it didn't quite find its original course and had to cut through a new part of the gorge. All right, so that's the three little vignettes I wanted to tell you about today. Basically telling you the story that bedrock is really important for understanding both the size and shape of the Finger Lakes as well as the differences we see between the different gorges. That, for example, the areas where there was thick sediment that was very weak and easily eroded made the two biggest Finger Lakes. That we also see these differences in the joint patterns in the gorges, and that you need the sandstone or siltstone to be able to make these joints, and that's why we see them more here in Cayuga Lake than over in Watkins Glen. And then the story of multiple glaciations we can see in the landscape, that we can see in places like Fall Creek and at Enfield Gorge, the evidence that the glaciers have come through multiple times, that the rivers have had to cut through the sediments and through multiple glaciations. And this can explain some of the interesting features that we see as we walk up these gorges. But these are just, again, the tip of the iceberg of all the interesting things that you can learn from Art's book. I learned a great deal from reading it, and there are still lots more things that we could learn from using about the Finger Lakes area that Art also sort of illuminates in his book of some of the remaining mysteries that still need to be addressed. So with that, I'll stop and take any questions you guys have. Thanks for your attention. All right, go ahead.
Question. Watkins Glen, if that's a shale base, and Enfield has got the harder material because it's broken into segments and fractions, why isn't Watkins Glen wider? Because shale is softer, isn't it? So why would there be more erosion through Watkins?
That's a great question. So I should also mention that there's that generalization is true. I guess the point, do we have a picture of the Watkins Glen thing here? Let's see if I've got that map. The other story, I guess what I'm trying to say in terms of looking at the width of the gorge is how long has the river had to cut it open? And so the idea at Watkins Glen is that might be, in general, the area it's cutting right now is it's the first time. It's only been cutting there for 10,000 years, while here at Lower Enfield, we don't know how many times, but it's been 2 or 3 times longer at least. So the rock composition is one part of the story. The other part of the story is how long has the river had. Other questions? Go ahead.
The picture of the stress lines that cross
Mm-hmm.
and across New York State have certain vectors that seem to come back to somewhere near Long Island. It's like an epicenter of that. And I was under the impression that perhaps that's North Africa hitting North America.
Exactly.
Right around there.
Exactly.
Now, the vector, does that relate to shock waves that are thrown through the bedrock, or is it a compaction?
In general, it's a stress state in the rock, and so the idea is that right now our stress state has a different orientation because of the plate tectonic forces that are on us. But during that time period, as you say, it was North Africa pushing into us. It had an unusual shape, just like the bends in the Appalachian, right? It has this big bend that goes through Pennsylvania. But that stress state was pushing this way, and so the maximum extensional stress was sort of perpendicular to it. So it was easier for joints to open this way and they certainly wouldn't open in the way that, if you're pushing it on this way, it's easier for joints to open this way. And so that's why, so what you're seeing here is basically a map of which was the area that was being pushed on, and this is telling you the area that it was easiest to open with. And so as you say, it sort of had this, North Africa had this shape that had, you could sort of follow it orientation like this, where the push was coming more in this direction over here, and over here the push was coming more in this direction here. Does that make sense? And so the other interesting thing that this map doesn't show, though, is that, we often see joints that are perpendicular to these, right? So this is one set of joints, but most of the gorges around here, we see more than one set of joints. And one of those other sets of joints are related to small folds that also formed as a result of this pressure from North Africa coming in. So we didn't get, the very large valley and ridge topography they have in Pennsylvania. We have this gentle series of folds that we can sometimes see exposed in the gorge walls. So if you look, there's a great picture in Art's book looking over from the yacht club towards the east, showing one of these folds in the side of Cayuga Lake. And that's what's shown here in this blue line, is there's an anticline related to this pressure and the folding of the rocks. And this folding process, when you get to the top of one of these anticlines, also causes extension. And so those are sort of perpendicular, related to this folding process, to the orientation that was related to the pushing of Africa into North America as well. So that's why you have two sets of joints in many of the gorges, and at least locally, that's why they're usually perpendicular to each other.
That's the fir tree anticline.
That is the fir tree point anticline, exactly. A very famous anticline, especially related to the Cargill salt mine over here, which takes advantage of that anticline, where the salt is locally a little bit thicker than it is in other areas.
One of the reasons I asked a question is I hiked Organic Park recently, and they put new signage up near their new visitor center. And there's a map that looks like this, except I think someone has actually sort of redrawn it from the original. And the vectors are not following this very
simple pattern,
standard
yeah.
pattern that you see more. The vectors are going right left. It's like someone decided to take a pen and go in and change those around a little rather than use the original data. And I don't, it kind of changes the story when you change the directions of those lines.
Right, well and you can see even here that there are a couple of different variations. So, looking at just this generation of joints, it makes the story a little simpler. But of course, the Appalachian Mountains were built not out of just one collision, but multiple collisions. So there was the Taconic orogeny and the Acadian orogeny and the Alleghanian orogeny over spanning tens of millions of years. And so each of those collisions came from a slightly different direction, and so that's also part of the story. So I guess the real world is a little more complicated than just this picture shows, but when you go to the gorges, it's usually, there's only one or two of these things that are usually dominant in any given area. And so that's why it sort of looks like this, as opposed to having joints in every which way direction.
So at least one of the orientations is no longer felt to be to glacial uplift or post-glacial uplift.
Well, the joints are also related to that as well. And so this is probably, as you can see, the dominant source of stress dates back 300 million years to when Africa collided with North America. But there are some joints, probably a minority, I don't know what percentage, but that are related to other sources of stress that are related to, as I mentioned, the buckling, as well as to the weight of 2 kilometers or 3 kilometers of ice pushing the crust down and then melting away also causes at least a small amount of stress near the surface that causes some of the joints to form. But I don't know if they've been mapped out in such a beautiful way as this. Great, go ahead.
I'm curious because I understand that Cargill Salt has salt caverns all the way out under Tunkhannock Falls State Park.
That's right.
And so is that under the bedrock or where?
It's
all under the lake.
That's right. So I don't know if I've got a great picture of it, but let's see. So it's in the bedrock. It's in the sedimentary rocks that were deposited. So I guess you can sort of see here, maybe. So this is showing, again, a profile through Cayuga Lake with Ithaca down here, showing, again, all of this is sort of sediment that filled up the lake. But if you look below the lake, again, here's this Onondaga limestone, this strong rock that sort of kept the glaciers from carving too deep. And under here, you'll see what's called the Silurian. The Silurian is a time when New York, when we formed our salt deposits. The salt deposits that you can see exposed in Syracuse, that you can see, that are also exposed, there's a salt mine under Lake Erie near Cleveland as well. That's also in these, again, it was part of a shallow sea. The sea more or less dried up during the Silurian time period. That's what they're mining. It's about 2,000 feet below Lansing where the Cargill mine goes in. But again, they're taking advantage of that deposit, for a good, as you said, up to Taconic Falls State Park, more or less.
Talking about Taconic Falls, why down by 89 the valley is so wide, but as you get up to the falls, just it's a narrow area. It's a change in the rock or what?
Again, I think it's probably just a history of how long is the river, and Tagonic's a good question that Art addresses in the book too, which is the question of how many times has the stream had to cut that huge gorge that goes all the way up to where Taconic is right now? And I don't think we have an answer for that. Like Niagara Gorge, we think it's just one shot. That's just the most recent glaciation has cut it back to where it is now. But you look at any of these other gorges around here, and we don't have, Ithaca Falls, for example, down here has not cut that far up into Fall Creek Valley. It has a nice wide amphitheater around it, which indicates maybe that's been multiple times of it cutting away. But here, I think, I can't remember if Art came down on a specific point of view on this as to whether Taconic is multiple cycles of the stream having to cut it back to where it is right now. But I think that's got to be the explanation there, is that this is an area that the gorge is a little bit wider here because it's had multiple times to erode apart, and that each time the glaciers leave, it has a little more time to work its way upstream and to make the gorge a little bit wider. But I think that's the simplest story I can think of for what's happening there. Great. All right, well, thank you guys all again for your attention. I'll take your question afterwards. Thank you again.